let's move to the basics of probability. So today we are going to talk about a basic framework which will model a probability experiment. What do you want to achieve using probability? Our main objective in probability theory is to compute the chance of an experiment, or more precisely, compute the chance of an outcome in a experiment where the outcomes are randomized in some sense. So this is what we want to achieve. For example, if I think of experiments, it could be tossing a coin, it could be throwing a dice, or it could be picking a random number from the interval 0 to 1. I have chosen 0 to 1, but it could be any other interval. And these are the examples of some experiments. And in these cases, the outcomes we might be interested in are, let's say, head when we toss a coin, occurrence of a prime number when we throw a dice, or when we are picking a random integer. When we are picking a random number between 0 and 1, let's say the number is bigger than 3 by 4. So these are the kind of outcomes we might be interested in given an experiment. And in high school, we had a very basic rule which said that the probability is equal to number of favorable outcomes divided by total number of outcomes. And most of the questions were solved applying this formula. What we need to do is to define the words in this formula more precisely. So our next goal is to define words like favorable outcome, even the word outcome, experiment more rigorously. This is what is going to be our first aim. And this is done by something called the sample. So the first observation we are going to have before we define sample space is that for an experiment, we really do not care about the physical implementation. When we toss a coin, whether Amitabh Bachchan is tossing a coin or Dharmendra is tossing a coin, is it on the top of the roof? We don't care. We will mostly bother about the possible outcomes. So in all these cases, the outcomes are heads or tails, except when it's tossed by Amitabh Bachchan. But let's assume that it is heads and tails. And then, what is the chance or frequency or the probability of these outcomes? As a mathematician, these are the interesting things to us. So this is what we care about. Physical implementation, we won't bother. Okay. Once we know this, then the importance of sample space kind of comes out. What is a sample space? It is just the set of all possible outcomes in a randomized experiment. So we want to model a random experiment. So first thing is to say what are the outcomes we can achieve. Mathematically, sample space is a set and is denoted by the symbol omega, big omega. To start with, you can think about the sample space for tossing a coin, throwing a dice, or our favorite experiment of picking a number between 0 and 1. So in all these cases, what is the sample space? Pause the video and make sure that you can figure out the sample space here. Once we have defined the sample space, the next thing is events. Mathematically, it is just a subset of a sample space. I should say sample a subset of the sample space omega. Intuitively, it is the set of things or outcomes whose probability we might be interested in. You remember, like a prime number or two heads or these kind of things. So all of these could be events and not just elements of the sample space. A thing to note here, most of the sample spaces in this course are going to be discrete because this is a course for computer science and mostly we encounter discrete sample space. And for this case, the probability can be modeled easily. So let us model probability for this case. When the sample space is discrete, the important thing is what we call a probability distribution function. Remember, we wanted to model an experiment. We started with sample space, events, which were all the subsets of the sample space, and finally, last but not the least, probability distribution function. This will model our probability event completely. So what is a probability distribution function? Not surprisingly, it is a function from omega, our sample space, to real numbers such that it satisfies two properties. One, if you look at the probability of any element in the sample space, it should be in 0. And second important thing, if I sum this probability over all elements of sample space, then this should come out to be 1. So any such function is a probability distribution function. This way, we will model our experiments where the sample space is discrete. We will talk about a more general framework in the next lecture, but let's stick to it at this point. So remember, to model, we need sample spaces, sample space of the experiment, then the events are all possible subsets of that sample space, and then we talk about probability distribution function, which is a function from omega to the real number which satisfies these two properties. This is a complete model of a probability event in probability. To start, you can think of an example. Suppose we toss two coins, or let's change it. We toss a coin twice. It has 10% probability of getting tails, let's say. So it's a slightly biased coin towards head, and we are interested in finding the probability that we get two consecutive heads. So we toss this coin twice and we want the probability of two consecutive heads. In this case, you should figure out what is the sample space and what is the probability distribution. This should be our goal in almost all the probability problems. Given any probability problem, your first goal should be to figure out at least mentally what is the sample space and what is the probability distribution function. Let us take a more practical example. Suppose your cousin is a gambler and she proposes the following thing to you. She will pick a random number between 1 to 1000. You can say that you have cards on which 1, 2 up to 1000 are written, and you or she will pick a random card. If the number is divisible by 2 or 5, then you win. That means she pays you 100 rupees. On the other hand, if that doesn't happen, if the number is not divisible by 2 or 5, then you will pay her 200 rupees. So Question is, should you accept this? Again, you pick a random number between 1 and 1000, and then if the number is divisible by 2 or 5, then you get 100 rupees. If the number is anything else, then you lose 200 rupees. Would you want to place your money on this kind of a bet? Our first goal should be to find the sample space. The sample space is pretty simple in this case. It is a set of all numbers from 1 to up to 1000. These are the all possible outcomes we have. And then the next step is to find probability distribution function. Again, we assume that all the numbers come up with equal probability. That means probability of omega should be 1 over 1000 for all omega in this sample space. So W would range from 1, 2, 3 up to 1000. For each of them, the probability is this. This implies that probability of a subset of, let's say, T of the sample space, this would be the size of T divided by 1000. And what T are we interested in? T is the set of all numbers n such that n is divisible by either 2 or 5. Now, as a small exercise, you figure out that the size of T is 600. So this is something which you can figure out. This implies that you get 100 rupees with probability 3 by 5 and lose 200 rupees with probability 2 by 5. Your winning probability or odds is 3 is to 2, but you lose in 2 is to 1 ratio or 4 is to 2 ratio. That means you should not accept this bet, and obviously your cousin, proficient gambler, is trying to trick you. So you should not accept this bet. The simple question, but again, make sure that you understand how we define the sample space and probability distribution function. Once we have these basic things, we can talk about probability of more complicated events. What happens to union of events? So let's say A and B are two events. You remember that these are subsets of the sample space. So then if someone asks you what is the probability of A union B, intuitively it is quite clear that it should be equal to PA plus PB if A and B are disjoint. This does not come as a surprise. So make sure that you intuitively understand it. But in a more general case, we can say that PA union B is probability of A plus probability of B. But this means that we have taken the probability of some events more than once. So we subtract. And as an exercise, prove this. Remember, we had this definition that probability of a set is just the probability of all the elements in the. So once we have the probability of an event, it should be easy to calculate probability of A in event. So this was a simple example, but now we might be interested in finding out probability of A union B union C. In this case, our first guess would be PA plus PB plus PC, which would be true if all these three events were disjoint. But you see that we are calculating or adding probabilities of events more than once, which were in both A and B. So if the sample point was in both A and B, then we are adding it twice. If a point was in all three, A, B, and C, then we are adding it thrice. Shouldn't do that. So let's correct our estimate, subtract all these probabilities. But now you might want to check. So what happens if the element was exactly in A and B, but not in C? You would see that I would count it here and then subtract here. So that is counted exactly once. That's okay. But what about if there was an event which was in all three, A, B, and C? Have we counted its probability correctly? It is counted in this, 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 and then again subtracted thrice. So that means it was not counted. So then the correct thing would be this expression. And you can check that all cases are covered. This actually gives rise to a formula which you know as inclusion exclusion. The formula says that probability of union of some events, you take summation over all possible sets and calculate the probability of each of these intersections. If this notation is new, then pause for a moment and just make sure that for n equal to 3, this formula gives rise to this expression. So I'm just writing this formula more generally with a new notation. So it should be fine to you. It is just I'm calculating A1 union A2 union A. What is the use of this? Mostly we use this when we say that, let's say, A1, A2, AN, these are the probability of some bad events. So A1 is a bad event, A2 is a bad event, AN is a bad event, and we want to find the probability that no bad event happens. So can you write this? No bad event happens. That's set mathematically in terms of A1, A2, AN. Take it as an exercise. It's not very hard. You realize that it is, if you take the union, which for which we actually wrote down the formula, and take the complement of it. Remember, A1, A2, AN, all these were bad events. So this tells us that no bad event. Then we are interested in this probability that no bad event happens. This is 1 minus probability AN. And we know this expression. Actually, we can think of 1 as probability intersection I is element of phi AN. This would be my claim. I would say that if I take the intersection over the empty set, then my probability should be 1. The idea is that as we take intersection of more and more elements, then the probability decreases. If I am taking intersection over empty set, that means there is no intersection, then the probability should be maximized. So this you can assume as a convention, or you can convince yourself that this is 1. This makes sense. Intersection of one elements decrease. So for least number of elements, the probability should be maximum, which we call it to be 1. So using this, we get the probability that no bad event happens. This is the quantity which you are interested in. This is summation over S. Now we can take summation over all possible subsets. I will just show you the expression. This was, so when I take 1 minus this thing goes out and we get intersection I element of S. So this is our formula for no bad event happening, where A1, A2, AN are all the bad events. I will finish this lecture by looking at an example for this. And this is the case when you have n letters and n envelopes, or both of them are numbered 1 to n, so there is only one correct envelope for one letter because of this numbering. And we are interested in the probability that no letter goes to the correct envelope. So we place the letters arbitrarily, randomly. So every permutation is equally likely. That is going to be our sample space. And the question is, what is the probability that no envelope goes to the correct letter? So the first thing is to define are bad events. So our bad events are the ones when actually the letter goes to the correct envelope. So that means AI should be the event that the ith letter goes to the correct envelope. So now to apply this formula, we need to figure out, and if you notice, this means that exactly, not exactly, but at least this many letters go to their correct positions. So that means these letters go to their correct positions, remaining ones I can permute them independently. And then the total number of permutations is n. I would like to tell you the meaning of this because this is a confusion for many students. When this happens, that events in S definitely happen. But for events which are not in S, we have no idea. That means this is not the probability that exactly events in AI are happening. This is the probability when events in S definitely happen, but outside S, we have no information. So given that, we figured out that in the case of letters and envelopes, this probability becomes this. And then applying the formula of inclusion and exclusion, we get that no envelope goes to correct position. So I'm just going to substitute this in my formula derived earlier, and I will get summation s minus 1 to the s and then n factorial. Now you realize that this quantity only depends on the size of s. So then this can be simplified to, and we have n choose k success of size k. So we get this formula for inclusion exclusion. It looks like 1 minus 1 by 2 factorial plus 1 by 3 factorial and so on. So if you do some bit of analysis, this approaches 1 by 3. So as n becomes close to infinity, the probability that no envelope goes to the correct envelope, no letter goes to the correct envelope becomes 1 by 3. So we saw one way to model probability experiment using sample space and probability distribution function. And remember that this was the case when the sample space was discrete. It turns out that this is not the most general framework. In the next lecture, we will see that we need a more general probability to tackle more cases, especially when the sample space is discrete, and we will see it next time. Thank you.